right, Pat, I'm not really going to introduce myself. I'm Diane. This is going to be a survey of some things that I've learned and experienced using Postgres as an application backend. So I'm thinking of this kind of as EMIC, user research from somebody inside the group. My goal today is to leave you with a useful model for thinking about the application development use case from the specific perspective of what I call the accidental DBA or database architect. This is a phenomenon I've seen many times, repeatedly with myself. I've been in the industry for about 20 years, starting as a back-end application developer and sort of circling the drain of database work until I finally fell in for good about, I don't know, 6 or 7 years ago. So we're going to explore how our accidental DBAs and architects traverse the software development lifecycle and look at the things that make persistence easier with Postgres and also the things that make it harder. A lot of the same base principles do, of course, apply to any other DBMS. This is just difficult to begin with, and applications do have kind of a specific nature that makes it even more fraught. So I say accidental, and I've worked mostly in very small companies, very small organizations. And in that context, or in places where people are wearing a lot of hats, you have development teams that need to handle persistence all by themselves. And smaller organizations are most organizations. So just like insects make up 50% of the biomass on the planet, smaller non-data specialist companies working with small data, building systems on databases that don't have billions of rows or terabyte tables, vastly outnumber the data specialists and the household names put together. And even those smaller systems do still tend to be too big for one person to hold in their head to be fully conversant with every component. Sometimes you get an operations team or some other division of responsibilities that can assist you with running the software, but schema design, performance analysis, and schema evolution are all completely self-service. So this also can happen no matter where you are in your career. Years of experience is not up on the board. But fundamentally, this is all about not having enough time to learn, time to experiment, time to grow. So this also does mean it's temporary. You do get through it, but there's no structured program for growing past this accidental phase. Also, even experienced database designers, I like to think I'm one at this point, we may pride ourselves on taking the time to get it right, but again, small organizations, you're wearing a lot of hats, that's often just not true. We'll skimp on analysis, we'll cut corners, and find ourselves making the exact same kinds of mistakes that a novice would, plus a few more because we're more dangerous because we know more. But there are a lot of different ways to use a database, and many of the challenges of persistence are common across all of them. So our first question is kind of, what is an application to us? So many uses of a database involve a person or some automation that connects directly to the database, does something, and departs, or stays connected permanently in some cases. But an application, to me, is something that mediates this connection. It brokers something between the user and the database. Your person or your automation connects to the application, has goals defined by the application. So this allows the team producing the system to present a palette of more complex, more intricate actions to a larger potential audience who don't need their own direct login to the database. So there's a few main flavors of this. There's quite a bit of overlap. A lot of web apps use the REST or GraphQL API under the hood. But this is a, frankly, really liberal definition, and this principle of mediating for a larger audience does have some other implications. When we offer users capabilities from our system, we can't control when they use it or what exactly they use them for. This puts us in a regime that I think that's a lot closer to streaming systems than batch systems. So our users are going to expect the system to be available when they want to use it, for as long as they want to use it. Any promises we make to our users, to our stakeholders, are not about the database, they're about the whole system. The database is a core component, but it is not what users see, it's not what people think of themselves as interacting with. So compatibility and interface stability requirements also are at the level of the system, not the database. So this allows us to do some decoupling, which gives us some operational flexibility, also takes some away sometimes, unless you breach the boundary and allow direct access to the database for somebody. This usually ends very badly. Now that we've defined application, where do app teams who don't have in-house data expertise to lean on end up? And I like to think of this through the lens of vernacular architecture, which is a term that antedates Amos Rappaport, the psychologist and architect who wrote the book. But he's variously quoted as saying that 90 to 95% of all building is in some vernacular style. So he summarized 5 criteria that make it up, at least in his eyes, and the first 4 do apply, I think, very closely to software engineering. But there's also a very pronounced dark side to each of those for us. So I mentioned time constraints. That is still very much true. We are focused on the immediate requirements that we get. We want to execute to those. We want to bring our current knowledge, our current assumptions to bear on the problem. So it's very easy for us to think too short-term and to paint ourselves into a corner, even when we might have product guidance who are still working from the same requirements and the same information that we are. We do have some access to the bodies of knowledge that exist around database work, but attaining fluency in navigating and understanding these is not our top priority. We want to get the job done well enough in the time allotted. This is kind of the root of all evil. Linus Torvalds has the quote, good programmers worry about data structures and their relationships, but our conditions here really do privilege the code. We think about information in motion, not at rest. We're out of our depth when it comes to schema design, so we'll tend to think code first, cut the schema to fit. In the extreme example, we'll consider the database to be dumb storage and prefer building all of our business logic into a separate application layer. Besides thinking of the system holistically in technological terms, we're also subject to Conway's law and constrained to produce systems that map to the communication patterns of our organization. If those patterns are dysfunctional, and every organization is somehow dysfunctional, our system is going to be that way too. And mistakes here can be very, very difficult to take back. In particular, it can be really difficult for us to recognize that what we're doing demands us to be really active stewards of the data and to approach the requirements and complications or nuances that we encounter with a really, truly critical eye. Finally, the team can be very unfamiliar with just how expressive data models can be, or not realize how important certain elements are, and that's how you end up with databases that don't have a single foreign key constraint. So we'll tend to lean on the familiar, the things that we know about. We'll prioritize discoverability, and we'll avoid magic like triggers, even when a trigger is the best available solution for the specific problem. A lot of the time, we'll use lowest common denominator SQL rather than taking advantage of a specific Postgresism like arrays or composite types or regex operations. So that's the 4. Rappaport did have a 5th criterion, open-endedness to further change, which is kind of just table stakes in software. Okay, we're not actually going to build an application, I'm lying. But if we were, most changes to how an application operates imply simultaneous changes to storage and vice versa. So we're in the business of automating interactions with the database. We will automate these too. Fundamentally, the schema evolution tool is a directory of scripts and a log table stating which have been applied. This has some really huge advantages for us. It allows us to stand up databases that are guaranteed to be structurally identical to production. So we can have local environments for development. We can have testing and staging environments, basically push button and deploy. So then we need something to talk to the database, and that's it, right? Nah, we need more software. So just like with evolution tooling at the data access layer, there are a ton of options for each of these categories, and everybody's situation is unique. So we have to ask ourselves, do we need a standalone pooler, or can we get by with the implementation in our driver library? And there's no one answer to this question. But the really scary part is that we don't know we need these up front. When we're working locally, the database is fine. It's basically in single user mode. So if we're new to operating databases, it's really easy for us to miss that these other three are super important to have up front. The database is a machine for organizing data, but that organization happens in phases, here in application development as elsewhere. The main difference from other forms of data work that I've run into is this focus on automating interactions on behalf of the larger user audience, which requires a large, very closely coupled code base. So we are pretending to build an application. We are on our first run from implement through to automate. So the things that we decide at this stage are going to have an outsized impact on every subsequent loop through the development lifecycle. We get requirements. We hope they reflect real user needs. There's no guarantees about that. What is guaranteed is that they are going to be evolving faster than we can code. So our conditions on the ground that we're working to are shifting under us. However, these requirements are our only guide to representing the problem, representing the parts of it. But because we think from code, not at first from a position that prioritizes where the data are going to be most of the time, we don't make good decisions here. We're not really set up for success when we start working with persistence. There are many problems that are not unique, probably most of them. For instance, if you're doing something geospatial, you probably picked Postgres because you know about PostGIS. Similarly, pgvector is sort of a killer app for the ML and vector embedding use case. But there are a lot of extensions that aren't well known. Foreign data wrappers, fuzzy stir match. I know the community currently is doing a lot of discussion and work around discoverability and availability. David Wheeler has been doing the summits. So I'm really looking forward to what's going to come out of that, because extension is a fantastic attribute of Postgres, allowing us to save a lot of time as long as we know that somebody else has already done the work. When we mediate on behalf of users, we usually do this very simply. I've seen some application databases that do make heavy use of different roles and assumption and row-level security, but I don't think it's nearly as widely used as it could be. When we get into data modeling, Postgres has fantastic capabilities here. There's composite types, there's arrays, there's JSON. Wait, there's JSON. Do we need to make any decisions here? Can we just treat this like Mongo? I've seen people do it in prototyping. It's obviously very bad once you care about your data, and I've found that you tend to start caring about your data sooner than you think. But my favorite page on the wiki is "Don't do this," and it's almost entirely about modeling problems. How do you work with time? What are the weird nuances of text? Should you use money? This is part of that body of knowledge that we don't have fluency with. We're not used to navigating. It's part of the Postgres sphere, not application development sphere. So it's a resource that we might as well not have access to in a lot of ways. Finally, we are in kind of a double bind between the capabilities Postgres offers us and the capabilities of the code we use or write to talk to the database. So Postgres knows about composite types, for example. Does our data access layer? Well, there's one way to find out. When we start actually using the database, we find that application developers do not want to write SQL. And I'm going to say something a little controversial here. I think they're right. The weaknesses of SQL are a whole other talk, but applications in particular have specific needs that SQL doesn't really meet very well at all, especially around dynamicity, select lists, criteria, ordering. This is all difficult, and there are further difficulties. SQL injection is the perennial top contender for the most financially damaging application security vulnerability, where you're just interpolating user input directly into a statement and you don't escape it, and somebody escapes it for you and then does a few more things on top. Finally, also, JDBC and its kin in the driver space are very low-level abstractions. And as application developers, there is nothing we love more than high-level abstractions. So this leads us to building high-level abstractions to talk to the database so we don't have to. So application developers started building data access layer software to organize and standardize interactions with the database in ways that are aligned, again, with our practical needs, our local idioms, our traditions of software development. And these new abstractions are basically lossy models of how a database works. They're honestly very useful, they're very convenient, but there's a problem with them that just as we hide the database from users through our system we build on top of it, the data access layer hides the database from us. We learn the abstractions, we don't learn the database. In the beginning, the Earth was without form and void, and we hand-wrote SQL and stuck it in our application code wherever. Hopefully, we would use prepared statements to prevent SQL injection. Hopefully, we'd organize this some way. No guarantees. This was a bad time, and I'm glad it's over. So some people recognized that this is a bad time, and frankly, I think they don't get as much credit as they deserve. But this is the original NoSQL. We have standard patterns of marshalling data into application usable shapes and then back out. So let's automate those and make it more convenient. And this was convenient. It was a great start. It was safer, better organized, but of course it had the near fatal flaw that relations just are not classes. These also introduce a dual data model where you have to recapitulate your table structure in classes, maintain both of those, keep changes synchronized, deal with the inevitable asymmetry. So big improvement, but still highly, highly flawed. So when you have something like that happen, there's going to be a reaction. And in fact, there were two reactions here. Both of them took a very similar approach to the question, which is, well, relations aren't classes. What if statements are classes? And this actually works a lot better because it adds a layer of decoupling in how you're talking to the database, and you're not joined at the hip anymore. The data mapper tendency on the left can even defer to the schema of the database, or at minimum, your second model represents the shape of your statement inputs and outputs rather than the tables themselves. Many of the query builders do want you to recapitulate your entire data model so they can offer compile time checks, which I have feelings about. But both of these do offer similar conveniences to ORMs. They just take slightly different approaches to how statements are generated. All right, I know it looks like I'm calling these throwbacks, but Dryopithecus was way later than Proconsul. These take the stance that, all right, in the beginning we handwrote SQL, and that was good. We should handwrite SQL. This is really what we want to do, is the most expressive possible approach to communicating with the database. It should just be easy to do a better job than it was back in the beginning. So these, you handwrite SQL, it runs your queries, it returns results in a convenient format. Are often unopinionated on where you run the SQL, so that's still a little bit up to you. These are also extremely useful. Remember I said we love higher order abstractions. To abstract over to build another data access layer, both of my projects in this space use PGPromise under the hood, so I don't have to do all the low-level result stuff myself. And then we have the weird ones. So these are your application. You don't really have a backend separate from them. They can be extensible, some of them. You can write plugins to modify the API or add functionality that isn't easy to do in Postgres, which heresy, I know, but there are a few things. Everything else, though, is a client. So some of these produce a REST API, some do GraphQL. They all build an internal representation of the schema by introspecting pgcatalog and stand up something that can receive HTTP requests over it. As we understand the March of Progress image from which I stole 4/5 of these now, evolution is not about linear improvement, it's about adapting to the environment you find yourself in. There's a lot more out there than ORMs nowadays, and developers, in my experience, who don't have that background with your Hibernate or what have you, are more than willing to try others because everybody knows about the impedance mismatch at this point. But when we consider our choice of tool to communicate with the database, again, we're looking at our place in our environment. So we ask again, are we going to have the 20% category of problems that ORMs just can't support? Or how much of a business logic layer do we really need? How comfortable or how fast can we get comfortable writing SQL? So we have that, we have our practical needs, our traditions that all inform our choice. And as usual, there is no one answer. Testing is especially important for application developers because the system that we work on comprises many different subsystems that interact over shared state in the database. So to understand our environment as we grow the system, we need legibility into how it works. Many languages do have test harness libraries that can exercise our code, including SQL. PGTap is fantastic, but we're building a lot of stuff on and around the database. So we're going to be bringing these other things in, but there's also one thing we can do, borrow from the database, potentially. There are a lot of catches here. Transactional testing is fantastic when you're connecting, doing something, and leaving, because it allows you to do anything you like and leave the database pristine, as if you'd never run anything. But once you're testing at the request to response level of granularity, this is kind of out of the picture. You can't roll back at that point. So you're going to have tests that have to contend with leftovers. We also do a lot of more complex workflows, and if you test those in parallel, you can deadlock yourself if you do something wrong. So this is not as great a tool as I would like it to be. Applications combine individual operations into these more complex workflows on behalf of our users. Every flow, every operation within that flow has conditions and prerequisites that govern whether it's going to execute. So here we don't have complete validation of this flow without going through both branches start to finish, but we can test isolated behaviors to identify problems more quickly, to prove functionality, especially if we extract something out for reuse elsewhere in the code base. But the biggest issue we have with testing is that this flow does not exist in a vacuum. Everything an application does, or almost everything, builds on other things the application has done. So before we can test most of the things that we need to, we have to get the test database ready. We have to get it into one of arbitrarily many expected states that are prerequisites for the flow under test. There are a few ways we can attack this problem. We can turn the problem of data pollution around, use it to our advantage, and the leftovers of the first test are the inputs of the second test. This is easy at first, but it's extremely brittle. You have to run your tests in the same order every single time. If you have an early error, you're going to have a bunch more failures to sort through also. So it's not a very good option. We could maintain testing data sets and just apply those, run the test, apply a different one, run a different test. This works. It's high effort, it's high redundancy, and you have a problem of minute variations that make a big difference. Also, if once you start evolving the schema, making some changes to how the application works with data, those changes either break your tests or they don't, which is worse because your tests no longer guarantee what you think they do. We could write individual setup code and stick it in each test suite. This is complete testing data sets, but messier. Finally, there's my favorite, the mini fixtures, where we write small modules that handle inserts into specific tables or closely related groups of tables, and then orchestrate those in the test case or by defining a dependency graph in the fixtures. So we can do minimal bespoke setup on top of that and get the flexibility of individual setup code with minimal redundancy. This is a surprisingly rare approach. I've only seen a couple other examples of it. The Doctrine PHP ORM offers it, and Doraj Eldink talked about it offhandedly in his talk about testing teardown at PGD Chicago. But despite our best efforts, we do still get bugs. Postgres exception messaging is generally quite good. It's very specific. It gets you into the documentation. Tony Typoulos had a study back in 2021, error messages in RDBMSs, which showed Postgres leading the pack, but there is, of course, always room to improve. Hints especially are great, and I would love to see more of them, especially in the era of, I don't want to say friendlier, but at least more helpful tools like the Rust compiler that is really, really expressive with, here's what you might be doing wrong, and here's how you might want to fix it. We do also only get the first error. This record has many more problems. So we're going to have to iterate to solve this thing and get this record into the database for real. It is very good to fail fast. We do feel it a little bit more on the application side because we have long workflows and a lot of setup. And then there's this, which is actually still a very good case if it is in fact a test failure, which it is here. So the change has not gone live yet, we hope, but we thought we would have one result. We have a different number. So if something isn't working how we expect, could be the database, could be something in the code. We have to go on a bit of a journey to rule out the other things and then start figuring out what behavior we've encoded in the database is incorrect. And the more complicated the database side of the equation is, the more difficult this gets. Diagnosis requires finding out exactly what executes, starting from the application code that's generating statements and making the queries. But especially once you get into functions or triggers, which does happen, there is a point where you have to go behind the curtain. When you go behind the curtain, you find logs. These are a little bit annoying. They're very noisy. You have to restart the entire server to adjust them, so hope you got it right in production the first time. Sometimes, especially if you're in a platform as a service context and you're in an ephemeral environment and haven't wired up pgbadger, it's a pain to get to them. There's also no statement logging in functions, so the only information you can get out of a function is through raise, and raising an exception only gives you the last frame when we're also interested in the call stack, which describes how we got there. This, I feel like, is probably just kind of a fourth-gen language problem, but the thing that I miss most from when I got started was with SQL Server is the profiler, which is a beautiful, fantastic tool that just blows grepping logs away in terms of giving you legibility into what's happening in your database. Here with Postgres, we can grep the logs, or we can just select star from pgstat activity as fast as we can. Redgate, I understand, has a new project, PG Now, which I think basically does the latter, if I've read the docs correctly. But this lack of legibility, or of easy legibility, really impairs our ability to understand, to reason about, and therefore to respond to problems. pgadmin and dbeaver have debuggers. I found this out, I think, less than a year ago because I use PSQL. But all of these debuggers require shared preload libraries and a server restart. So again, you're not doing this in production. You're going to have to recreate the conditions of the problem locally. This can be painful. You have to get your data organized just so, and only then can you trigger the fault. On the plus side, doing that is basically a test protocol, so you can guarantee the fix. And we do have potentially a head start with our fixtures, but it can still take time, be a substantial effort. And then there's what I do. This is a lot faster because I push this button, the thing breaks. So log into production, /EF, just raise warning here, raise warning there, raise warning everywhere. And I say raise warning advisedly because raise notice is too nice. Some log levels just skip it. And again, we don't want to restart, we're in production. You might also be thinking, what about notify and listen? I thought about notify and listen when I first ran into this kind of problem. And then I found out that notify is transactional, so if you have an error, nothing gets delivered. This notably does not produce a real test. It's very bad on that count, but it's very fast. Speaking of very fast, much like execution debugging, performance is another venture into the unknown wilds of the database as its distinct and very self-contained subsystem. And we find that performance changes phase very, very suddenly and unexpectedly. Usually when we are neck deep in something else and really do not have time to deal with this right now, thank you very much. But something can get popular, the query planner can decide, there's too much of this in this table now, I'm not going to use that index. But it should really have been using the index. And then we have to read some things very quickly and start digging into statistics. But when this happened to me, I read some things very quickly, dug into statistics, found out what had happened. I learned a lot, and I was under a lot of time pressure. Time pressure is very bad for forming memories. So I forgot almost all of it and had to start over from square one the next time. This does feel like an area that's really ripe for tooling improvements. We have explain helpers from Depeche, PG Mustard, and others that give you the what, but not the why. With Postgres 18, we have external explain modules, and Andrei Lepikov posted last month, I think, about some recent experiments he's been doing, augmenting explain with stats, which is super exciting. I'm really looking forward to more stuff coming out of that. Performance is always a production issue. There's just no substitute for baseline load on the database. Other people are talking to it too. The volume of data is very difficult to replicate. Frankly, the perversity of the data, it's your imagination against the world's. You are not going to be able to come up with half the things people actually store. So performance analysis, performance troubleshooting is a process of experimentation in production, which is a little bit nerve-wracking. We just have to try things and see what happens. Concurrent index builds are wonderful for doing this without incurring downtime, but concurrent index builds are about all we've got. There's no way to force a query planner, force the planner to use an index that we know better in some rare cases. And there's a lot of clever tricks you can apply to a SQL statement to divert the planner, to distract it, to make it think things are not what it expects, and use a better plan. We don't have that because we use high-level abstractions that generate SQL statements, so that's just completely off the table for us. So if the planner has issues with one specific table or even one way of addressing a specific table, well, we could disable hash joins for the entire database. We are never doing that. So, okay, we've tested, we've debugged, figured out performance, but we're going to have to change the data model. Well, crap. So schema design was really high impact when we didn't have any data. Now we do. That's a problem. We have also potentially, urgency. This stuff always happens under time constraints. We could also be either recovering from or entering a new practical need over theoretical rigor situation. It's got to get done or it's got to get undone very quickly. And also it has to get done synchronously with an application update. So we can make a lot of really important guarantees around how a change is executed. Transactional DDL may be my favorite thing about Postgres. Being able to have complete confidence in atomicity of schema changes is just an incredibly reassuring feeling, and one that makes me much more scared of working with other databases ever again. We do have some tools around idempotence that do have understandable limitations, but are also lending themselves to some interesting developments in schema evolution tooling that I unfortunately don't have time to talk about. We can also incur a little bit of risk of divergence and preload some longer running changes like big index builds. So do that manually, throw in an if not exists in the evolution script, and we skip the build when the thing officially goes live. So it's often worth it because we don't want to be in limbo for hours while the thing goes. Sometimes, though, we're in limbo for hours. So DDL is transactional, which is great, but if we interrupt in the middle of a series of changes, we're still in what's effectively an inconsistent state with what the application expects. Existing data has inertia, and a lot of existing data has a lot of inertia. I've had to be the person who says, well, we have committed to this thing going out now, so hold your horses. It's not fun. The Postgres project has put a lot of work into minimizing the effects of this and the chances of encountering it. The add column change in Postgres 11 to add a column with defaults without doing a full table rewrite was huge. But it's also not just about the inertia of the data. We also have the inertia of the application code base to contend with, and it may be stateless, but it still has weight. Calling back to Goofus and Gallant, Goofus slings DDL directly into production at the same time as he rolls out a new version of the application, eats a little downtime, hopefully nobody notices. Gallant makes things complicated, or rather, things are often complicated, and Gallant recognizes this. This is the expand and contract pattern, where we support two ways of doing something temporarily and then remove the old way. We're starting to see some automation around this with projects like pgrole, pgosc. It is, I think, fairly early days yet, and there are some interoperability questions with other frameworks. I know pgrole wants to be your one and only schema evolution tool. But also, many changes are really one shot. It's expand only, there's nothing to contract. So this sort of slower, more careful, more effort-intensive approach is overkill in a lot of cases. All right, we're almost done. There are many reasons Postgres is a favorite in the database world. It's certainly my favorite. So what makes the application developer, accidental DBA, user base unhappy in its own way? Application developers, application teams think in application terms. We expect to own and operate the database, to control the schema, to be able to move quickly without having to work things out with some other team. We deal with evolving requirements. We expect to be sort of the one-stop shop for that rather than having to get other interests aligned and coordinated. Also making the leap from the basically stateless or at least ephemeral world of application code into database work is just really tough. The analytical tools that we have available to us are different and in many ways more limited. Analysis about what's going on in the database requires a lot of reasoning about how the database should be behaving, which is a skill that you just have to build, and it takes time. Performance transitions are sudden and bumpy. They can require urgent response under a lot of pressure without any kind of band-aid fix being available to help us just sort of limp onward. And the reasoning aid, we don't really have yet any reasoning aids when it comes to the arcane of statistics and figuring out why the planner is making the decisions it does. In general, also, it's really difficult to tell how long something will take without just doing it. Applications don't just represent the automation of interactions with data, they embody it. The database is at the core of what they do, but it's very much a core component versus a standalone interoperating quantity. The high-level abstractions over SQL are not going anywhere. The query runner species of data access layer is very useful in many contexts, but I don't think it's high-level enough to take over because people are coming into this expecting an interface that looks like applications and libraries that they're familiar with, rather than making the jump immediately all the way over to SQL. So these needs and expectations really are not liable to change anytime soon, and we're going to continue to see databases built often by non-experts in a vernacular style that doesn't use all of the affordances the database software offers, and that prioritizes immediate needs in the immediate context without devoting as much thought and consideration as ideally we would to extensibility and future-proofing. Obviously, I'm here because I think this user base of the accidental crowd working in the vernacular mode is important and has specific needs that are worth paying attention to. So the question then is, how do we do this? How can the Postgres community reach people who are unfamiliar with our resources, who are working under time constraints and can't build familiarity easily? How do we meet them closer to where they are right now? So, as with every other question I've asked, there are many answers here, but I think the tooling gaps and the apparent limitations from the application developer side deserve all the attention that the community is giving them right now and more. But longer term, this is also going to require supporting learning and growth through this accidental phase, because it is a phase. And that's extremely difficult for a community that's as decentralized as Postgres is. We have the manual as a central resource. I think that is necessary but not sufficient, because data modeling, whether done professionally or in this vernacular mode, is an art. And the manual can't and shouldn't teach an art. It's about identifying and negotiating important boundaries, working out relationships, making decisions about reducible and irreducible complexities. Postgres at this point is the default free and open source RDBMS. The community, in my experience, has mostly been focused on teaching the nuts and bolts of operating it and using it. And we often seem to assume that people already know, already understand how it fits into their larger scale goals. So last question, I don't have answers, sorry. This isn't that kind of talk, is how do we teach people to situate Postgres in context and build effectively to their own purposes, their own goals on top of it? Thank you.